There's one other part to section 3.4, and that this part isn't really tested as much in Delta Math, but it is something that is helpful. It's called the second derivative test. So we actually had a first derivative test, and our first derivative test was when we checked to see if a first derivative went from positive to negative or negative to positive, and that's how we tested to see if we had maximums or minimums. Well, the second derivative test is actually another way to figure out if a function has a maximum or minimum by using the second derivative. So here's how it works, and we'll kind of talk through it. Um, what you're going to do is you're going to find all your critical values, just like you did at the beginning of the chapter. You're going to take your first derivative, set it equal to 0 or undefined, and list your x values. But instead of setting up intervals and seeing what's happening around each interval, which can be very time consuming, we're going to instead take each critical value and plug it into the second derivative. That's why we call it the second derivative test, because we're actually putting that critical value into the second derivative. Here's what will happen. Either you're going to plug it into the second derivative and you're going to get a positive result, and that proves that that x value is actually a minimum. And you might be looking at this going, why is a positive a minimum? Here's why. Second derivative, if a second derivative is positive, then the concavity looks like that. It looks like a U, it's a concave up. You'll notice that the extrema on that is a minimum. So if it has a second derivative that's positive, it's going to create a minimum. If it has a second derivative that is negative, any negative, doesn't even matter the number as long as you know it's negative, then visually it would look like this because it would be concave down, which means it would create a maximum. Now, here's the only downfall with this test. If you take that critical value and you put it into the second derivative and you actually get 0, you don't get a positive number or a negative number, the test fails. And what that means is there still could be a minimum or maximum, but we don't have enough information to know that. So we have to revert back to what we did in the beginning of the chapter. So it's not a fail-proof test. There is a time when it doesn't work. But for the most part, it's actually a really quick way to figure out if we have extremas that are minimums and maximums. So as far as why does this work? Well, it works because the concavity gives us an idea of the shape. And if we know the shape, we know what type of extrema. Why would I want to do this? That's usually the number one question students have is, I learned something before, it works really well. Why do I need this? It's faster in certain circumstances. If it's something that you really don't want to set up intervals because there will be so many intervals, or if it's something that has some really ugly numbers when it comes to intervals, sometimes real life problems, the intervals aren't so clean cut, then this is just a faster way to go about it. And it just gives you another option. So let me show you how it works. I'm going to do 3 questions. So the directions will say something along the lines of use the second derivative test to determine if my extrema, my minimums or my maximums. So my first thing is I need to get my critical values. So I'm going to take the derivative. So 6x squared minus 6x minus 12, set it equal to 0. I can take out a 6, which is going to give me x squared minus x minus 2, which is going to give me x minus 2x plus 1, giving me critical values of positive 2 and negative 1. So using the old approach, you would set up intervals and you would test those intervals and see how does it switch, increasing, decreasing, or vice versa. With this, we're just going to go to the second derivative. And I wouldn't do this if it was a really difficult second derivative, but this is a very easy second derivative. Polynomials are the best ones to do this with. So my second derivative is 12x minus 6. If I put 2 into that second derivative, I get a positive number. I'm not even going to write the positive number. I'm just going to write positive because that's all I care about. That tells me that 2 is a minimum. If I plug negative 1 into my second derivative, I get negative minus 6. I get a negative, which tells me it's a maximum. Now to find the y values, I do still have to go back to the original function. That doesn't change. So if I put 2 into the original function, I'm going to cheat and grab a calculator here. So 2 times 2 to the third minus 3 times 2 squared minus 12 times 2 plus 5, I get negative 15. And when I put negative 1 in, I'm going to get negative 2 minus 3 plus 12 plus 5. I get 12. So there are my minimum and my maximum. I would get the same answer had I done a first derivative test and set up intervals. This way, I don't have to worry about setting up intervals. If a question only wants to know extrema and doesn't care about increasing and decreasing, it's another time that this would be probably more beneficial to go this route. This one, my first derivative is negative 2x plus 4. Set that equal to 0, I get 2x equals 4, so x equals 2. That's my only critical value. My second derivative, you'll notice, is a constant. It is always negative, which means it's always concave down. So this has to be a maximum. This should make sense because this is a parabola that looks like this. It's a parabola that opens down. So whatever your critical value is going to be a maximum. My maximum happens at 2, and then I'm going to put 2 into my original function, and I get -2. So there is my relative maximum. So that's like best case scenario. Parabolas are very quick with these. Last one, I want to show you what do we do if things don't work with this test. So first derivative, 15x to the fourth minus 15x squared. Take out a 15x squared, which leaves you with x squared minus 1. So we have lots of critical values, 0, +1, and -1. My second derivative is 60x cubed minus 30x. 0 is going to create a problem. I'm actually going to deal with that last. I'm going to look at the other two that are nice. If I put -1 into this second derivative, I'm going to get a -60 plus 30. That's going to be a negative. So that's a maximum because my graph would look like this. And if I put +1 in, I would get 60 minus 30, which is positive. So that would be a minimum, again, because the graph would look like this. So I have my maximum and I have my minimum. Here's the problem with 0 and what we do for it. So the problem is if I put 0 in, I get 0, which means the test is inconclusive. I don't know if there's a maximum or minimum or nothing there at all. So here's what I have to do. I actually have to go back and look at what happens before 0, and I need to look at what happens after the 0 with my first derivative. And I'm only going, because I know things are changing at -1 and 1, I'm only looking from -1 to 0 as being what happens before and from 0 to 1 after. If I go back to my first derivative, if I put like -1/2 in, I will get a positive times a negative. So I will get negative, meaning it's decreasing. And if I put a half in, I still get a positive times a negative. So there was no extrema at x equals 1. Now, I have had students say, can we just assume if the test fails, it's not an extrema? No, there are actually cases where the second derivative test fails and it does end up being a minimum or maximum. Usually it's a funky minimum or maximum, like a sharp point, but it is possible. Let's go back to the original function to get my full coordinates here. If I put -1 in, I'm going to get -3 plus 5, so that's 2. So that's my maximum. And if I put 1 in, I get 3 minus 5, which is -2, and that is my minimum. This one, if you're wondering, like, what in the world does this look like? This is one where you have, you would have a graph that at 0, you would get 0, 0. So this is one, what does this look like? Let me graph it and put it on the screen for you, or at least draw a picture for you. So if you were to graph this, sorry, my calculator is giving me fits. So if you were to graph this, 3x to the 5th minus 5x to the 3rd, this is what this looks like. So it goes up to my maximum. It has this momentary kind of pause here, and then it goes down here to the minimum. So that doesn't show up really well. But at the origin, it has this flat region. So we do have a maximum here. We have a minimum here, and that's it.